So last part of chapter 1, we'll talk about data collection and sample data. Mentioned very in the beginning when we were talking about data that our methods are driven by the type of data that we collect. And the type of data can determine what methods we can use when collecting data and when applying treatments and when analyzing and displaying data. So being aware of the data that we're using is important. So there are two distinct sources or ways that we obtain data, and it's either a experimental study, okay, or an observational study. Okay, so an experiment or an observational study, those are two main ways of collecting data. The type of data we're collecting will usually lend itself to one or the other. Experiments, by their nature, are a little bit more scientific. They apply a treatment and then observe the effects on the individuals. Now, individuals is a very broad term. It doesn't have to mean people. It could be anything that we're studying. It could be plants, it could be animals, it could be birds, it could be marbles rolling down a hill. Okay? It could be whatever it is we're doing. Okay. So the individuals are called experimental units. If we're talking about people, then normally we refer to them as subjects. Usually, at least in a good experiment, another part of the population will be called the control group, which thinks they're getting the treatment, but they're actually not getting the treatment. Usually they are given a placebo, a harmless something, okay? So they think they're getting it, but they're not actually, okay? Placebo used to be just like a sugar pill, okay? But it doesn't necessarily have to be a sugar pill. It could be, just any type of harmless or fake treatment that makes them think they're the real treatment. So an example, we have an experiment performed on rats in which the treatment group was given a oxide, bonus point if you can pronounce that, in a substance that's present in seafood, while rats in the control group were just given water. Okay? Water is not going to affect their day-to-day life, anything different. So that is the placebo. Water was that placebo. After performing testing, researchers concluded that oxide reduced mortality rate related to heart disease in rats that had heart disease. Okay, so we had a group of rats, it's our population. They were given a treatment of this trimethylene oxide to see and then observe the results. The results was that the incidence of heart disease went down. Okay, that's an experiment. Now, a lot of times there are things that would be impossible to apply a treatment to, or more likely super unethical to do, or it's dangerous, or it's too costly. And in those cases, when we're trying to collect data, an experiment is not going to be conducive, and so we have to rely on an observational study. Observational studies just observe and measure specific characteristics without attempting to modify anything. So we're just watching and collecting data from things that happen as they are. Observational study was conducted in which researchers measured the amount of time period people spent doing various activities such as volunteering, paid work, childcare, socializing, and that's usually done through a simple survey. Okay? Most of the time, a lot of observational studies are just done with a survey. Problem with that is people aren't always the most reliable, and so you have to kind of take that in when you're looking at observational studies. They can still be a very powerful tool when we are not able to do an experiment because applying some treatment would be too expensive, too dangerous, unethical, whatever the case may be. So when we're determining whether or not we have an observational study or an experiment, the key thing is, was there a treatment applied? Okay? Was there a treatment applied? Or was something just observed? If we applied a treatment, okay, we modified something, then that was an experiment. If all we did was observe things as they happened, then we have an observational study. So, for example, one researcher studied the effect of vitamin D3 supplementation among patients who were newly diagnosed with a viral infection. To perform the study, researchers gave 2,700 U.S. adults either a daily vitamin D3 supplement or a placebo for 4 weeks. Is that going to be an observational study or an experiment, and why?
Experiment.
Why?
Because giving half the group an actual daily vitamin of vitamin D, and then other people.
Yeah. So they're applying a treatment. That's our treatment to a population or a sample. We also have a control group because some were given a placebo, which is great. And so because we have that treatment being applied to a sample, we have an experiment. Researchers conducted a study to determine how confident Americans are in the U.S. economy. To perform the study, they called 1,019 U.S. adults and asked them to rate the current economic conditions and whether it's getting better or worse. Experiment or study. There's no treatment. They called and they asked. Okay? They called and they asked. They performed a survey. So it's an observational study. Pennsylvania Game Commission conducted a study to determine the percentage of Pennsylvania elk population in each age and sex class. The commission captured and released elk during each year of the study and found an overall average of 16 branch bulls, 7% spike bulls, 56%, and 21% calves. Observational study or experiment?
Observational.
Why?
Well, it says study in the paragraph.
You can also have an experimental study. That right there is what you want to latch onto. They're not controlling anything. So does that make an experiment or an observation? They're capturing and releasing in order to observe. They're not applying a treatment. They're not giving the elk anything. They're looking at them and they're letting them go. So we have an observational study again. A couple of ways that we collect data, all right, whether we're doing an experiment or an observational study. We have a simulation. Simulation is the use of a mathematical or physical model to reproduce the conditions of a situation or a process. Okay? Simulation is a very, very powerful tool and most often what is used now in the digital age. We have some really, really good simulation model software that we can use. So automobile manufacturers use simulations with dummies to study the effect of crashes on humans. Have you ever seen those commercials where they ram it into a wall at the end?
Yes.
Okay, so they're testing their safety features. That is a simulation. They are simulating car crashes to determine how well their safety equipment works, how good their airbags are, how good their crumple tech is. Survey, investigation of one or more characteristic of a population, usually carried out by asking people questions. Most common, internet surveys, phone surveys, or interview, sometimes by mail. Census is usually done by mail. We're harassed by people standing outside a store, trying to collect a survey usually, or both. And with all of this data collection, it comes down to one simple thing. Not really simple, a lot of work that goes into it. But we're looking at the validity of the results. How much can we trust the information that we received? And how useful is it in whatever conclusion we're trying to arrive at? And so we're going to come across this concept of experimental design and looking at bias. So in order to get meaningful results, we want them to be unbiased. Experiments, surveys, observational studies, whatever it is, they need to be very carefully designed and executed. And to that end, there is actually a giant board of professionals that whenever you want to do an experiment, okay, you have to, and you want it to be backed and supported, you have to get it approved by this international review board where they look over your process to make sure that it is valid and it's ethical. That's the big part. They want to make sure it's ethical. And right, so we can do it. And it's important to know the steps that you take in order to make the results of an experiment valid. Control, randomization, and replication are those three main pillars. Control, randomization, and replication. When any of those fall apart, you are increasing the amount of bias in your study. Unless you get a full census, there's going to be some level of bias. Your job as an experimenter is to minimize that as much as possible. So the first factor, we're looking at control. We have what's called a confounding variable. When you cannot tell the difference between the effects of different factors, right? So, for example, there are some days where my face is a little scruffier than normal. And those are days where I also didn't get as much sleep. Okay? And so it's easy to assume that, well, the days where I get less sleep, my scruff gets a little bit longer. But what that doesn't take into account is, why did I not get enough sleep? It's probably because one of my two children kept waking me up in the middle of the night, or would go to sleep, and I chose to sleep in for an extra 10, 15 minutes rather than clean up the scruff on my face. So it's a confounding variable. To attract more customers to a coffee shop, you can remodel it with bright colors, but at the same time, something else happened. Shopping mall opened, it had its grand opening. So business increased. Was it because of the bright colors? Was it because of the shopping mall? Was it a little bit of both? Probably a little bit of both. Maybe. But we don't know, because there was other stuff outside of our control that could have influenced the results. So minimizing confounding variables, or at least identifying confounding variables, anything that could interfere with what's going on with the experiment. Placebo effect. Interesting and common. The human body is strange. And so people can receive a placebo, they think they're getting the real medicine, so they get better, even though they were given a fake treatment. The placebo effect. Now, some ways to counteract and help in control is a process known as blinding. So the subjects don't know whether they're given a placebo or a treatment. And when you do double blinding, not only is it the subject doesn't know, but the experimenter also doesn't know. It's all set up by a third party, okay? And the person who is administering the treatments doesn't know if it's real or fake. So that's what is often known as a double-blind study. Whoever's administering the treatment has no idea if they're getting the actual treatment or if they're part of the control group. They have no idea whatsoever. And then all that information is aggregated and then analyzed after the fact. And so then you know which individuals got which, only when it's completed. The second pillar being randomization. And there's a bunch of different ways to randomize the study. When we're randomizing, we are trying to just mix up the population as much as possible to get a good variety of traits in both the control group and the treatment group. We want to make sure that we have an equal number of men and women, young and middle-aged and old, employed and unemployed, well and sick. We want a good variety, preferably equal amounts of every type of feature in both the control group and the treatment group. So we randomly assign subjects to different groups. If we have a completely random design, you are assigned into a random group. I just take everyone in here and I give you all a number. And then I say, okay, numbers 1, 5, 7, 4, 6, 18. You all go to this group, and then everyone else goes to the other group. Just random numbers are chosen for each group with no consideration of anything else. More often, to help with confounding variables and other things, experimentals will use some type of a block design, where groups with similar characteristics are grouped together and then from there randomly assigned to treatment or control group. So a block design would be, I take all the men and I take all the women and I separate them. And then I randomly take all the men and say, okay, half of you go here, half of you go there. And then I go to all the women and say, okay, half of you go here and half of you go there. So that way I have an equal mixture for whatever that characteristic is. And so you can do it on age, you can do it on gender, you can do it on working status, you can do it on whatever. Okay? You can make these random block designs. So you divide the subjects with similar characteristics and then randomly assign them to different treatment groups. We can also do matching pair design, where we pair everybody up with someone with similar characteristics. A little more time consuming, but you say, okay, well, you two are very similar in age and weight and height and gender and everything. Okay, you guys are matched, and then you guys are matched. You do that with every subject, and then one person goes to control and the other one goes to treatment. The last pillar is going to be our replication. And a lot of times what's important displayed in data is sample size. Okay? If I perform a study on you 20 people, okay, the results are going to vary if I perform the same study on a different group of 20 and a different group of 20 and a different group of 20. I would expect them to be a little similar, but it will vary some. Now, if I make that group larger, and I perform that study on 40 people, and then another 40 people, and another 40 people, those differences from sample to sample are going to get smaller the larger my samples get, because we've got more randomness and more variability within the data. And so being able to repeat an experiment under same or similar conditions can improve the validity of the result. Whenever you read any experimental study that's released, any paper, any scientific paper, there is a very detailed account of how they did the study so that someone else can copy it and compare their results. And they say, we got 150 people from this geographic region with these characteristics, and we applied this treatment in this amount, this often, and we measured the results this many times at these specific intervals. It is very, very detailed and very, very boring, unless you want to do the study yourself, so that we can follow under this replication. Can you do it again? There have been many, many studies that have been even newsworthy, but they were not able to be replicated, and so then they fall flat. Okay, because it was a fluke. So, being able to think critically and looking at an experiment and this actually is something that's really, really useful because a lot of times you will see news articles or headlines or TikToks or whatever where they state some fact. A new study found, well, that if you eat 5 times a day, you'll lose 20 pounds. Like, whatever, something stupid. Okay? But something that seems reasonable, but is very, very hyped or inflammatory or something. Well, those headlines are designed to get views and clicks and watches, okay, and likes. But they often leave out the importance of the experimental design. And if you can actually look at that study and see how the experiment was designed, you can see whether it's actually valid or not. One of the most famous examples, and whether you believe it or not, I'm just going to give you the pure facts of mine. Okay. 10-ish years ago, I think, I can't remember, it's been so long, came out and said that he found a causational link between vaccines and autism. Okay, big study that came out. Vaccines cause autism. Right? But when you actually go and look at his experimental design, it was highly, highly flawed, and no one is able to replicate it. And that's just one case among many, 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 is that you need to be able to analyze the experimental design and be able to replicate it and get the same results. And so whenever you see something that makes you want to change a behavior, oh, if I eat a banana every day, I'll be able to sleep better. Take some time to look at the experimental design and analyze it and make sure, is it actually valid? I don't want to eat a banana every day to help me, especially if I don't like bananas. So, a company wants to test the effectiveness of a new gum developed to help people quit smoking. Identify a potential problem with each experimental design and suggest a way to improve it. Okay, so again, we're looking at control, we're looking at randomness, and we're looking at repeatability. The company identifies 10 adults who are heavy smokers. 5 of the subjects are given a new gum, and the other 5 subjects are given a placebo. After 2 months, the subjects are evaluated, and it's found that the 5 subjects using the new gum have quit smoking. What is a potential problem with that study?
5 of the smokers.
I would go ahead and assume that if they're participating in the study, they all probably wanted to quit. Because it's to study the effect of a gum helping them quit smoking. Hey, who's a heavy smoker who wants to quit smoking? We have a study to see if this helps. Could vary. So we want to control that. So you have to have specific dosage, which is a possibility. We don't know if they controlled it or not, but that's definitely a consideration. What else? It's like taking medication. Sometimes you have to take it at a specific time. Control that. What else? We looked at control. Identify some potential flaws with control, just making sure that it's regulated, the amount and the time. Okay. Randomness. Do you see any issue with randomness? Really? What about repeatability? Or replication? How big is that sample?
Small.
It would be very valid. Sample size is very, very important when you're doing a study. 5 people in your control group and 5 people in your test group. It's not a lot. So while there may be some instance of, yeah, this might work, how well it works, you're going to need a much, much larger sample size. So the biggest issue here would be to increase your sample size. If you only have 5 subjects testing something, it's not very many. It'd be 5 of you to determine what the class average is. All right? It's not a very good representative sample. So the company identifies 1,000 adults who are heavy smokers. Okay, now we have a much bigger sample size. Much more reasonable. Now the subjects are divided into blocks according to gender. Females are given the new gum and males are given the placebo. After 2 months, a significant number of the female subjects have quit smoking. What's the issue here? They only gave it to one of the blocks. What should they have done? Randomize the groups. There's nothing wrong with doing the blocks. Doing the blocks is a really good idea. Split the men and the women, okay? Or whatever feature you want to do. You can do it by age, okay? Age or gender or both. You could do a combination of those blocks. But then split and give half the females the treatment and the other half the placebo. And then give half the males the treatment and the other half the placebos. So after they got the blocks, they should have randomized the control group and the treatment group from those blocks. All right, last thing we're going to cover is sampling techniques. So again, sample is a part of the population. Okay, so count or measure a part of the population that we use in our statistical studies. We usually can't test it on everybody, so we just get a part of it. To collect unbiased data, we want to ensure that the sample is representative of the population. Again, if I want to figure out what the average GPA of a Mumford Academy student is, and I only took your 19 GPAs, it's not necessarily representative of the population. First of all, you're all seniors. So I'm leaving out 3 different grade levels. Okay? And then the variety of courses and students that we have available, it's not very representative. So appropriate sampling techniques will ensure that inferences about the population are valid. We want to make sure that if I make an assumption about you, it applies to everybody. The better I have in my sampling, the more likely that is going to happen. There will always be some sampling error. It's never going to be perfect. That's why a lot of times when you see studies that says 20% of people approve of whatever, you usually see a little plus minus 3% or something next to it. That's the sampling error. They're saying that there's going to be some error by this much above or below whatever our estimation is. So a biased sample is one that's not representative. A sample of consisting only 18 to 22-year-old college students would not be representative of all 18 to 22-year-olds because they are completely leaving out anyone who didn't go to college, anyone who chose to just go straight into work, or someone who went into the military. You are excluding an entire section of the population by only including college students between the ages of 18 to 22. So you have to look very carefully at what your population of interest is and make sure it applies to them. Now, if your study is just looking at how much college debt the average 18 to 22-year-old has, well then yeah, looking at only college students makes sense because anyone that didn't go to college is not going to have any debt. But if you're looking at something broader, like how much money the average 18 to 22-year-old makes, you need to include all 18 to 22-year-olds. Not just college students, not just workers. You need to include the entire group. So at the very basic level, we have a random sample. Random sample is every member of the population has an equal chance to be selected for the study. And a simple random sample means that we could mix up all the groups and we could take it over and over and over, and all the groups have an equal chance of being selected. This is usually done by random number generation of some kind. Random numbers can be generated by a table, by using a software program, by using a calculator. Every member of the population is assigned a number, and then that random number generator is used to pick people corresponding to the numbers that they were given. Number of people who live in Westridge County, to use a simple random sample, they count the number of people who live in Westridge County households, assign a different number to each household, and then use a random number generator to get a selection of numbers to choose from. So that's a very, very common one if you want to get an easy, unbiased sample. Doesn't require much extra work, but it still gives you some fairly unbiased results. If I wanted a simple random sample of Montverde Academy students, I would probably, you've already got numbers assigned to you as your student ID numbers. So I would just use a random number generator to pick some random student identification numbers and then include those students in the survey. Now, the rest of them have to do with some type of grouping for the most part. So stratified and cluster are pretty similar. Stratified is we divide populations and groups based on some characteristic. Okay? Income, gender. Geological, well, that's not geological, that's going to be more cluster. But some feature of them we use to kind of break them up into strata. And so with the Westridge County example, they broke up the households into low, middle, and high income. Cluster samples break them into groups based off of kind of a location, and then they just select everyone in that one group. All right? So with a stratified, we're picking people from every single group. Okay? We're picking people from every single group in a stratified. In a cluster, we break everyone up, and then we just pick one. Okay? And so a lot of times with geological, it works well because we say, okay, we got a good mix of our population here, and here, and here, and here. Okay, let's just take this zone. And we'll include that in our sample. Systematic. You choose a starting point and then you do something, you do like a random interval. Okay, but more at a pattern. And so we'll start at, some specific number, and then we choose every 5th or every 10th. Okay? So a lot of times a store, if they want to do a survey, they'll ask every 10th customer. Okay? They start at some point, the manager walks out, picks a customer, asks a survey, and then waits till 9 more people walk out and then asks the next person. And then wait for 9 more people to walk out and then ask the next person. And so that's a systematic sample. We pick a starting value and then an interval to keep adding to the sample. Convenient sample is the worst. It's whatever's easiest, whoever's available. If I were to survey all of you, that would be a very convenient sample. You're here, you're trapped, okay? I can get your information, okay? Only members of the population that are easy to get, and that leads to the most biased results. So let's look at these 3 and identify the sampling technique. If we're doing a study to determine the opinion of students at your school regarding stem cell research. So our first option is you divide the student population with respect to major and then randomly select and question some students in each major. Is that going to be a simple random sample, stratified, cluster, systematic, or convenient? Divide them into groups based on major, select students from each major. So be stratified. Okay? The major, those are our strata. We broke them up into groups based on a feature. And then we chose someone from every major. Okay? Sample from each group. That's going to be our stratified. You assign each student a number and generate random numbers. You then question each student whose number is randomly selected. Simple random numbers. And here's the people. You select students who are in your biology class. Convenience. It's easily available. The first two will provide some pretty valid results. The last one will not. Right? It will be probably very, very biased.